The heading indicator, also known as the directional gyro or direction indicator, is a flight instrument used in an aircraft to inform the pilot of the aircraft's heading. The primary means of establishing the heading in most small aircraft is the magnetic compass, which, however, suffers from several types of errors, including that created by the dip or downward slope of the Earth's magnetic field. Dip errors cause the magnetic compass to read incorrectly whenever the aircraft is in a bank, or during acceleration or deceleration, making it difficult to use in any flight condition other than unaccelerated, perfectly straight and level. To remedy this, the pilot will typically maneuver the airplane with reference to the heading indicator. As the gyroscopic heading indicator is unaffected by dip and acceleration errors, the pilot will periodically reset the heading indicator to the heading shown on the magnetic compass. The heading indicator works using a gyroscope, tied by an erection mechanism to the aircraft yawing plane, i.e. the plane defined by the longitudinal and the horizontal axis of the aircraft. As such, any configuration of the aircraft yawing plane that does not match the local Earth horizontal results in an indication error. The heading indicator is arranged such that the gyro axis is used to drive the display, which consists of a circular compass card calibrated in degrees. The gyroscope is spun either electrically or using filtered airflow from a suction pump, sometimes a pressure pump in high altitude aircraft, driven from the aircraft's engine. Because the Earth rotates 15 degrees per hour apparent drift, and because of the small accumulated errors caused by imperfect balancing of the gyro, the heading indicator will drift over time, real drift, and must be reset using a magnetic compass periodically. The apparent drift is predicted by sin latitude and will thus be greatest over the poles. To counter for the effects of Earth rate drift, a latitude nut can be set on the ground only, which induces a, hopefully equal and opposite, real wander in the gyroscope. Otherwise, it will be necessary to manually realign the direction indicator once each 10 to 15 minutes during routine in-flight checks. Failure to do this is a common source of navigation errors among new pilots. Another sort of apparent drift exists in the form of transport wander, caused by the aircraft movement and the convergence of the meridian lines towards the poles. It equals the course change along a great circle, orthodrome flight path. Variation. Some more expensive heading indicators are slaved to a magnetic sensor called a flux gauge. The flux gauge continuously senses the Earth's magnetic field, and the servo mechanism constantly corrects the heading indicator. These slave gyros reduce pilot workload by eliminating the need for manual realignment every 10 to 15 minutes. The prediction of drift in degrees per hour is as follows. Although it is possible to predict the drift, there will be minor variations from the basic model, accounted for by gimbal error, operating the aircraft away from the local horizontal, among others. A common source of error here is an improper setting for the latitude nut to the opposite hemisphere, for example. The table, however, allows one to gauge whether an indicator is behaving as expected and as such is compared with the realignment corrections made with the reference to the magnetic compass. Transport wander is an undesirable consequence of apparent drift. Gyro pressure gauge, vacuum gauge or suction gauge are all terms for the same gauge, used to monitor the vacuum developed in the system that actuates the air-driven gyroscopic flight instruments. Air is pulled through the instruments, causing gyroscopes to spin. The speed at which the gyros spin needs to be within a certain range for correct operation. This speed is directly related to the suction pressure that is developed in the system. The suction gauge is extremely important in aircraft relying solely on vacuum-operated gyroscopic flight instruments. Vacuum is a differential pressure indication, meaning the pressure to be measured is compared to atmospheric pressure through the use of a sealed diaphragm or capsule. The gauge is calibrated in inches of mercury. It shows how much less pressure exists in the system than in the atmosphere. In order to overcome the major drawback of the Venturi tube, that is, its susceptibility to ice, aircraft were equipped with engine-driven vacuum pumps and the gyro instruments were driven by air pulled through the instrument by the suction produced by these pumps. A suction relief valve maintains the desired pressure, usually about 4 inches of mercury, on the attitude gyro instruments, and a needle valve between one of the attitude indicators and a turn and slip indicator restricted the airflow to maintain the desired 2 inches of suction in its case. Totally dedicated to Carol Ramona Patterson. Love you forever, Mum.